Pittman, and this is my talk, Natural Language Processing in Java. So I'm a developer experience engineer at Google, working on the Android team. I currently work in deep links, so if you want to talk to me about that after the talk, by all means, find me, that's great. This talk actually has nothing to do with my day job and is something I do entirely for fun. So natural language processing. What is it? So what you want to do with what natural language processing is you are trying to come up with human responses to human text. It's ways of analyzing free-form text information that let you draw knowledge from it and perform some action on it and then feed that back to the person. We're going to talk a little bit about how it works, some of the history of it, and we're going to talk a little bit about some of the modern tools and techniques that we use, specifically the Apache OpenNLP project. So how does NLP work? Well, you see there are aliens, and the aliens live in the computer, and they just do all of the knowledge for you. I don't think anyone here believes me, so let's try again. It's magic. There is magic in the computer. That's why whenever the magic smoke comes out, it stops working. I have a feeling that you don't believe this either. All right, so the truth is that it is neither aliens nor magic. It is actually just math. So in the history of NLP, there have basically been three large techniques that people have used. There's been symbolic analysis, which ran from about the 1950s until the 1980s. If you've taken a compiler class, you'll feel right at home when we talk about that. What symbolic analysis is that you're actually looking at the individual words. I say you. The computer is looking at the individual words, and it's looking at a lookup table. It is figuring out what it's supposed to do in response to that word, and it moves on. If you have ever used a terrible chatbot written in the 90s, it was probably using a symbolic method of generating natural language processing. Starting in the 80s, computers stopped being slow and stopped being expensive, so we started being able to have statistical methods. And we're going to talk a little bit about statistical methods when we talk about OpenNLP. What statistical methods are is it's a way of analyzing word frequencies and word patterns inside of free-form text to try and associate it with different outcomes that users have provided to the machine for it to look for. And we'll get into that a little bit later in the talk. And the current hotness is neural processing methods, which use machine learning and convolutional neural networks. I don't know those, and we're not going to talk about them. No matter which method you do, though, what you really want to have happen when you're working with natural language is you want to have some sort of pipeline. And in this pipeline, the first step is you normalize your text. What I mean by normalize your text is you get rid of all of the extraneous formatting or extraneous information. You format the text, you organize the text in a way that makes it easier for your computer to understand. Then you want to do something that's called sentence detection, which is breaking down large sections of text into smaller sections of text. And then finally, you want to get into tokenization, where you look at the individual words and the punctuation marks and things like that. And when I say you, I mean the computer. And finally, we get to processing, and that's where you try to extract value back out of whatever process you are doing. So how does NLP work? Science. It is science. It is math. It is not easy because there's a lot of it, but it's understandable and it's something that humans can do. So this is an example of a symbolic model called Eliza. Eliza was invented in 1966 to be a Rogerian psychoanalyst computer program. If you've ever seen on television where someone says, oh, I had a terrible dream last night, and the therapist says, tell me about the dream, and they say, tell about the dream, and then the therapist goes, and what do you think that means? And the person goes, this is what I think it means. That's that type of psychology. It was invented in 1966 by a MIT researcher, Joseph Weisselbaum, and he worked on it for about 2 years, and there's a lot of really cool history in it. And if you ever get a chance to watch some YouTube videos or listen or read some of the original papers, I highly recommend it. We're about to talk about what Eliza is and how it would be implemented in Java using a Java program that was written in 1996 by a different researcher, Charles Hayden, who was I basically found it on his website. So this is an example of a conversation with an Eliza bot where it's just like it's doing what I said it was doing before, where Eliza prompts, tell me your problem. And, oh, no, wait, this is the symbolic model. Sorry, it's really small on my screen, and I got lost a little. No, this is the symbolic model. An example of the symbolic model that powers Eliza. So we're going to talk a little bit about models. Models are where computers store the information that it uses to process natural language text. In Eliza, they use a very simple hand-generated model that has, you know what, let me fix my screen so I can actually see what I am showing you guys. There we go, all right. So the Eliza model has several tags and then several words. So it has the tag for initial, which is, hey, this is an initial response that the computer will give. It has a final tag for these are the responses the computer will give when it's done. It has this quit tag, which is the words it is looking for to let it know that it is done, that the person has told it is done processing. And then there are several other tags that it has where words are detected in the text. They are normalized to standardized tokens. In the case of if you say dreamt, dreams, dreamy, Eliza will normalize that to dreamed. If you say your, yours, your, and various others, it'll normalize to mine. It has hand-coded synonyms. So belief, feel, think, believe, wish. These are all things that Eliza knows is the same word, and it gets normalized to a key that Eliza can look up later. Then once all of the text has been normalized, once all of the text has been processed, it will run through this key section where it's where if you had said you dreamed something, that's where this, I can't find my mouse. That is where this key comes in, and it identifies that, hey, someone said something about a dream, so here are some of the responses to give. What does that dream mean? What does that dream suggest? What do you dream? Do you dream often? What persons appear in your dreams? Do you believe that dreams have something to do with your problems? And like I said, it's trying to find a way to ask a question back to the user based on the input that they gave it. So in Charles's 1996 Java program, this is his normalization step. So there's this method called process input where you pass in a string. The string then translates any uppercase letters to lowercase. It strips out all of the punctuation. It turns any of the accent marks or symbols such as parentheses or hashtags or dollar signs, just strips those out, and it turns all punctuation into periods, and then it trims and removes all excess white space. So that's what it does. And now that it has a normalized string, it applies a basic matcher where it's functionally splitting on a period to generate the sentences. And for each sentence that it generates, it will try and come up, it will process that sentence and see if there's a reply. If there's a reply, it returns the reply and it's done. If not, it moves on to the next sentence. The translation step, so once it's processing the sentence, it translates it into that normalized form that I was talking about where common words are replaced with a single word that can be looked up later. And this is trying to match each word individually, and then it looks up in that table, in your model table, those words to try and normalize it. And then once it's normalized, it will, when it's looking up words in this table, it will replace whatever word it finds with a similar words. So if you say machines, computers, that gets replaced in the internal representation of Eliza with computer. And then Eliza can look up that computer word later in its own model to try and make a response. And this is the code that makes that response. So for each, the Eliza model is really, really long. So the key section is this right here. So what Eliza does, once it's tokenized your input, once it's normalized it, once it's made it into a form that it understands, it will start iterating through its key values in the model, looking for where that word is and seeing if it matches enough to make a reply. And that's what this code does. So the key section here for computer, if you had said, hey, my machine is messing up, it will know that your computer is messing up. It will normalize that to computer. It will find computer in the key, and then it will return one of the responses somewhat at random. So, you know, if you said my computer is messing up, it will parse that sentence, find the word computer, and will possibly respond with, why do you mention computers? Well, because it's messing up. Like I said, these things aren't that smart. And this is a example that I did. So if you remember from earlier, we had dreams getting normalized, and if we check back here, then you can see that there is the dreamt, dreamed, and then there's the key. So you'll expect if I say something about a dream, it'll be one of these responses in reassim, and that is what we have. One more here. So I had a dream about cows. What does that dream suggest to you? And then I have a computer. Why do computers worry you? And if I say I have a computer again, why do you mention computers? I have a computer. What do you think machines have to do with your problems? So not very smart responses, and just from a lookup table, from a handcrafted lookup table. And that's really all there is to it. It provides a human-like response sometimes, but the model has to be written by hand. It has to be created by hand. It's a giant lookup table. It's hundreds of lines long, and even though we've moved on from this technique, we've gotten techniques that have better responses, this is what we can still learn from, and it's what we can use for pre-processing our data, for making normalized forms of the data that we can feed into our statistical models, which is what we will move to next. So Apache has this project called OpenNLP, Open Natural Language Processing. It's really, really awesome. So it's at opennlp.apache.org. It provides several Java APIs and command line tools to ingest text data, to process it, to build your own models, and to try to perform some tasks that you assign it. It's a really big toolkit, and it provides models from several sources in several languages that are mostly newspaper source. So you have Spanish language models, you have German language models, you have English language models, and I believe you have French language models. And so what I wanted to do was demonstrate how you can use the OpenNLP models that are provided to try and gain information from something that is near and dear to my heart. Until recently, I was one of the organizers of the DevNexus conference in Atlanta. It's coming up in April of 2023. Registration is open, CFPs are open, so if you're interested, I suggest you look that up. And what our OpenNLP model will do is, hopefully, I will be able to give it the biographies of people who have spoken at DevNexus in the past, and it will just give me a list of names of those people who spoke. Oops. The DevNexus website is open source. You can go on the website. Go on GitHub and download the website. You can look at its code. You can run it yourself if you want. And what's great is the older conferences are still archived in there. Different sites had different designs, and there were all kinds of like small things. So this actually sounds like a really good case for natural language processing to run through the data and try and extract information from it. There is one caveat to this, and it's that we don't actually need natural language processing, and I'll talk about that in just a minute. So one of the things you need to know about the DevNexus website is that its format has all of the files for each year, for each speaker in a directory. I'm not going to show the code from this, but whenever you see me referencing a file, it is just one of these speaker biography files that's in 20-something directories in a kind of standard pattern. So I said in a moment that we don't actually need natural language processing for it. HTML data, which is how this data is stored, is actually a type of data called structured data, which means that it has markup tags, it has commands for an HTML processor, i.e. a web browser, on how to display it. And if we want, we can actually just use this library called JSoup to parse each file and get the H4 tag, which is the tag that the website uses to display the speaker's name. And if we actually wanted to do that, we could just grab that dependency with Maven, we run that code for each file, and it will give us the name of the speaker in that file. But we like doing things the hard, inefficient, and error-prone way. So we're going to use a natural language processing statistical model based on newspaper sources. And so how do we do that? Well, remember what I said at the beginning of the talk, that there's a pipeline you follow. You want to normalize your data, so we're going to strip out all of the HTML and just feed in the raw biography information. We need to break that information into sentences. OpenNLP provides a sentence model that can detect sentences and break them up for you. Then we want to break it into tokens. OpenNLP provides a token model that can break sentences into tokens for you. And then finally, we want to extract names. And once again, OpenNLP provides a name extraction model that has been trained on annotated data to find and detect names in natural text. We load up our models. Like I said, there is one for tokenization, one for sentences, and one for persons. Each of these are binary, immutable models. You can't open one up and look at it. It's statistical math. I mean, it's numbers and weights and analyses. You can't edit it. You can't grow it. Once you've trained a model, it is set. And so this is the part of normalizing our data, where for each file in our directories, we're going to use JSoup again to select the text of the biography body, which is where, you know, speakers have their biographies, where it says, I am Summers, I work at Google, I do this. But everyone has their own writing style, and some people say, you know, from Atlanta hails Summers, who works at Google. Or some of them don't even put their names in there, and the model just goes, there isn't a name. So there's a lot of stuff you can give to the natural language processing system, and a lot of information it can get out. Once we've normalized our data, we want to extract sentences. So we can use that sentence model to make a sentence detector, and then we can pass our text HTML, the raw, unformed text, into this detector, and it will return to us an array of strings that are individual sentences. And then we want to extract our name tokens. Just like with the sentence, we pass the token model into the token detector, and we tokenize each sentence. And then with that array of tokens, we can use the name finder that's instantiated from a name model to find the names of the text. So this is an example of a biography from the DevNexus website. Keith Donald is a principal and founding partner at SpringSource, the company behind Spring and the division of VMware, blah, 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 blah. This is from 2009 from our text. We run it through those three detectors, the sentence detector, the tokenizer, and the name extractor. And this is the output we get. We have everything correctly broken into sentences, and we actually have names: Keith Donald, Keith, and Keith. So in each sentence, these are the names that the natural language processing model was able to detect and was able to surface for us. And it's literally this. You have these three things to load your models. You extract the text that you need from your source. You pass it into a sentence detector. You pass the sentence into a tokenizer. You pass the tokens into the name finder, and the name finder does it. So let's try this again with someone else. Pratik Patel. He is one of the people who helped organize this conference as well. If you find him, give him a hug, buy him a drink. He's a great guy. So what do you think happens when we run this through our model? Do you think it's going to find Pratik? No, it didn't. So one of the things that's important to know about natural language processing with statistics is that the work it is able to do is highly dependent on your corpus of text, the text that your company is wanting to process, the text that your project wants to process. And so what you need to do is you actually need to train these models on your text. And we are going to kind of work through that right now. So both biographies were similar. If you look, both of them said Keith is a, and then went on, and with Pratik, Pratik is the, and then it went on. But there was something in the statistical model that made Pratik not match when Keith did. And so what we need to do is that we need to train the models on the corpus of text that is the DevNexus biography data. This requires a lot of data. According to the NLP project, you need about 15,000 sentences to begin to get a good training model. Fortunately, like I said, we have all of the data from DevNexus going back to 2006, I think. So this is what training looks like. You use tags that are this start and then the entity name, in our case a person. You surround it by a person's name, and then you just do this with one for each sentence. Where there's a person in there, you tag it, and when there's not a person, you don't. And you do this thousands and thousands and thousands of times. For this talk and for this example, I went through about 3,000 lines of biography data and tagged it. It didn't actually take that long. It took about 3 hours to do because people are really good at this and computers aren't. And so when you're ready to, wow, that is very small. I apologize. And so NLP provides methods for creating a model of your own from your training data, and it really looks about the same way. You break the model into sentences. In this case, it's just from the text. Each sentence is on a line. You feed it into your name finder model, or no, you feed it into your name finder model trainer, and you pass in some of the parameters that are in NLP. It generates a model, and then you can write this model out to a file using standard Java APIs. The way you use the model you just trained is the same way you use the model they gave you. You instantiate the model using their APIs, and then you run the name finder again. And so let's see what happens when we run our new model against the text that we wrote just now. So we see that it correctly identifies the sentences, which we thought it would because it correctly identified it before, and we didn't change that model. And what's even better is it found Pratik Patel as a name, and it found Pratik as a name. Now, when I generated this data, I intentionally left the 2009 DevNexus data out of the training set so that when we processed this 2009 post, it wouldn't be just finding something we had trained. It wouldn't be hard-coded or overfit to that data. So this is actually what the natural language model produces when we run it on it. It says Pratik Patel and Pratik. That's great. But it also says CSS3 and JavaScript, which are not people, I hope. Don't tell Elon Musk. He might name one of his children that. So, all right, what happened? Still, what's wrong? Well, like I said, NLP says you need about 15,000 sentences to get a good model, and I only did 3,000. So I did about 1/5 of the work that was actually necessary to do it. And also, when I was researching this topic earlier today, the OpenNLP has add-ons to the core library. And one of these add-ons is this thing called Default Model Builder Util, which makes it a lot easier to build these models. So I unfortunately don't have an example of this, but what the model builder will do is, in addition to taking in your sentences, it will also ask you for a list of things that you know to be looking for. So I could hand it a list of all the names of all the speakers from DevNexus, and it will just go ahead and automatically tag those when it runs through, which is great. It also lets you do a blacklist. And so what I can do with this blacklist is I can run an entire corpus of data through my model that we trained, and I have the good names, and then I have the stuff that's wrong. And I can feed into this utility class, in addition to the list of good names, the list of wrong names, and it will correct the model as it's processing so that the model doesn't get these false positives, which is really, really cool. And I'll probably make a demo of that and put it on YouTube sometime. Oh, wow, and that's the end. So this went a lot quicker than expected, and I do have some bonus content if people want to see. But this is a great chance to stop, and if anyone has questions, we can talk a little bit about that, because I got off to a little rocky start, what with video and some slides being out of order. So are there any questions so far? No? All right. So real quick, this is an example of a categorizer. So we had an entity finder, a name entity finder in the previous example. In this example, it's a categorizer. What's a categorizer? A categorizer is a spam filter. Except instead of saying if something is spam or not, it's if something matches some category you have assigned it to it. And this category can be anything for your document. You can say this document is spam. You can say that this document is a purchase order. You can say that this document is a resume. You can say that this document is a response to call for papers, or this document is someone having problems with registration. I helped organize a conference for a while, so I decided to run a categorizer on the emails that the conference inbox got to try and automate reading email. And so how do we do that? Well, we do it about the same way we did before. We create a training data set, we calculate a model, and then we test the model against our data. In this case, this is an example of my training set. The first token is the category that the email belongs in, and then everything after that is a normalized string of the email. So when the model runs, the first thing it does is it says, okay, this is the category. The category is a CFP response. And then it just ingests that whole email. It processes it according to the pipelines that we have talked about before, and it adds it to the model. And it does this for thousands and thousands and thousands of emails over the course of decades. And eventually, what you can do is you can start feeding it new emails, and you can ask it to guess what those emails are. So this right here is just, this is training. This is the training, this is the code that does the training. And again, it's really, really boring Java because all you're doing is you're instantiating a few objects, and these objects are doing all of the statistical analysis for you. Like I said, I'm not really able to speak at length about how the statistics work, but I can talk about how the APIs work. And then, once we have our model, once we've calculated our model here, then we can pass it into a document categorizer, and we can send each email into the categorizer to get a list of outcomes, which is all of the categories that OpenNLP knows about. It will tell you what the % likelihood that category is matching to the email. And you can even ask it for the best category given your outcomes, and it looks a little bit something like this, where I made a simple browser for all of these emails, and when I click on something that hasn't been categorized, it can tell us at the bottom of the screen its best guess. In this case, category is predicted to be a CFP, and sure enough, it's a CFP. What do we do when it's wrong? Well, we update the model, we update our training data, and we recalculate the model. You have to recalculate the model every time you update the training data. It doesn't take that long for 3,000 words, for 3,000 sentences, but for 15,000 sentences, it'll take a bit longer. And if you're someone like the New York Times, who has been running these types of jobs for years, it could take hours and hours and hours to actually calculate the models. And this is where kind of the more modern neural processing comes in, and they have specialized hardware, they have specialized tools, and so this gives you a slightly different behavior. And what's important about those is that they're actually like not self-learning, but they're more self-guiding. So it requires less of this manual annotation. So that's the end of the bonus content. And now it is time for questions for real. Does anyone have any questions? No?
Yes. Does OpenNLP has any APIs for unsupervised learning as well? Because all of these seem to be like in the tag data, right?
Does OpenAPI have any APIs for what?
OpenNLP has any APIs for unsupervised learning?
I don't think so. I think OpenNLP is, they might have an add-on for unsupervised learning, but in their core package, I didn't see anything for unsupervised learning. It's all tagged, it's all based around tagging your free-form text and training it that way. Any other questions? No? All right, well, thank you.
So Java conference, obviously, tutorials in Java, but Python is, the more, I think Python when I think of like NLP or machine learning. So does this package have comparable libraries in Python? And then how does, using Java for NLP compared to using a different language?
I don't think Apache NLP has Python libraries. On the webpage, they at least said it was a Java library. But if they might have add-ons, they might have other things, but I think this is Java exclusive. And how does Java compare to using Python for other languages? The short answer is I don't know. The longer answer is Python's a lot more of a dynamic language, and it probably is able to be a little bit more concise and a little bit more expressive. If you look at some of these, if you look at our source code, it's very laborious, very imperative. It's very, very Java in its look and feel. Yes.
What is the accuracy level of this?
Pardon?
What is the accuracy level of
the accuracy level? It depends. Like when you're talking about accuracy, what are you have to know kind of what you're asking for. So it's as accurate as the data you give it, and it's as accurate as the amount of data you can give it. So in this example, it was very accurate. It found Keith's name everywhere, but the default model couldn't find Pratik's name. And with a partially trained model, we were able to find Pratik's name, but we were also getting a lot of false positives. And that's where this model builder util would come in, where we can give it, hey, here's all the stuff we're expecting, and it can model, and it can tag that data itself, given this is a green list, and then it can untag things that it finds using the black list and update the model that way. So the answer to your question is, unfortunately, it's as accurate as the data you trained it on. And if you're modeling, say, receipts, it can be very accurate because it's very repetitive, very standardized data. But if it's somebody's biography or if it's newspaper articles, then your accuracy is directly proportional to the amount of data you train it on.
Sorry, can go ahead.
Yeah, so there would be names which also could be nouns, because somebody would just use names just like that, right? So how would the model understand, and how would the blacklisting work at that point?
So how does it understand that, like, if your name is Car, how does it know you're talking about a person named Car and not a vehicle? So without getting into a lot of details that I'm not qualified to talk about, the statistical model looks at pairs of words, it looks at chains of words, it looks at the parts of speech that words can be in, and it uses all of that extra information during calculation to figure out whether or not this car is a person or not. Have I seen if it's seen car as a person a lot and seen car as an automobile a lot, and you're using the person's name car where you'd use a person's name, then it's great. But if you're using the person's name where you wouldn't use a person's name, then it might accidentally think that it's a car instead of a person. But it doesn't have to be explicitly trained. So when I made my Pratik, with my Pratik demo, Pratik's name does not appear in the source data set. But because I trained it on the biography data, and Pratik's biography was typical of a biography, it was able to find his name in that data. So car would be about the same way. And I could probably look through the data and find better examples of that, and we could actually step through it later.
Thank you.
Yeah, I just want to know, are there any options to select the algorithm underneath while we run like tokenizer or any inferencing models?
So you can, are you asking if there are other models you can choose from? Or like, can you do more?
Inference, like we can use like multiple algorithms, right? Underneath, like it could be standard deviation inference or like any other thing. Like, can we choose the algorithm underneath for inference or?
I don't know. So
The open NLP supports that.
yeah, I don't know. I know that you can pass in a bunch of models. I don't know if it can like automatically choose from different ones or give you ways to choose during runtime. Like, I mean, you can obviously pick a different model if you don't like the results of the first one, like we do here. But I don't know if there's a way to automatically do it or compare models in OpenNLP. All right.
Is there a generative model like GPT-3 where you can give it a fragment of text and it'll use the model to like predict how it would continue?
I don't think so. I don't think it has generative models in it, but that's a good question. And
are they doing anything with context-aware models?
I'm not sure. Maybe. You'd have to look at the OpenNLP website. Cool. Any other questions? Going once? Going twice? All right. Well, thank you. This was a lot of fun. I do this for fun. I'm not a professional natural language guy, so this was really, really great, y'all. All right. Have a good rest of your conference.